In section 7.2, we'll pick up our first gas law, which connects trends in gas volume to pressure at constant temperature. We'll see how the law was developed, then use it to solve problems. I hope those algebra skills are fresh. Let's begin. In the 1600s, Robert Boyle discovered that the volume of a given sample of a gas at a constant temperature is inversely proportional to its pressure, meaning as one quantity goes up, the other will go down. For example, increasing the volume of a gas sample at a given temperature by a factor of 2, so doubling the volume, results in the pressure decreasing by a factor of 2, being halved. If you watch the Boyle's Law video in figure 7.3, it replicates the last slide, but as an animation. Imagine we collected data to replicate Boyle's work. What mathematical relationship could we build between pressure and volume beyond saying they're inversely proportional? Take a minute to look at the data. Do you notice any trends? When an inversely proportional relationship exists between variables, we see that multiplying those variables together yields a constant value. We can restate Boyle's law as PV equals K, where K is this constant. What if that relationship wasn't immediately evident? Then we'd have to graph the data to unlock its secrets. Graphing the volume versus the pressure, meaning that the volume is graphed as the dependent variable on the y-axis, and pressure is the independent variable on the x-axis, gives us this disappointing, rather saggy little curve. Chemists don't deal well with nonlinear graphs, so we are famous for torturing the data to give a straight line because we all still recall that y equals mx plus b is the equation for a straight line. Well, the organic chemist might not remember that, but you get my point. A straight line on this 1 over volume versus pressure graph shows the data is related in an inverse fashion. So keep that in mind if you have to graph any pressure volume data. All right, let's get Boyle's law into a form where we can use this as a tool to discover pressure-volume relationships. If we consider that the pressure and volume of a gas at a constant temperature under one set of conditions equals a constant, K, then we can change that sample of gas from one pressure, P1, to another, P2, at constant temperature, which will be reflected in the volume change from V1 to V2. This gives us P1 V1 equals P2 V2 at constant temperature. Let's try some calculations for practice. A 3.50 liter sample of hydrogen gas has a pressure of 0.750 atm. I want you to stop right there and start labeling quantities with their respective variables, as I've done in the table shown. Next, we're looking for the volume, V2, when the pressure is doubled to 1.50 atm at constant temperature. To solve for V2, we need to rearrange Boyle's law, P1V1 equals P2V2, so that V2 is equal to P1V1 over P2. Plugging in the data, we get V2 equals 0.750 atm times 3.50 liters divided by 1.50 atm. Solving, we get V2 equals 1.75 liters. Now ask yourself, at the end of every question, does this result make sense given what I know about the concept? In this case, because we know Boyle's law is an inverse relationship, if we double the pressure, we expect the volume to decrease by half. 1.75 liters is indeed half the volume of 3.50 liters, so it looks like our algebra checks out. Here's one for you to try. A 1.45 liter gas sample has a pressure of 0.950 atm. What is the volume after the pressure is increased to 787 torr at a constant temperature? Make sure you convert torr to atm first so that the units cancel, then report your answer to 3 significant figures. Here's the answer. First, we have to convert torr to atm. P2 equals 787 torr divided by 760 torr to get 1 atm equals 1.0355 atm. I've left some extra significant figures in this intermediate calculation so I don't introduce any rounding errors. We rearrange Boyle's law, P1V1 equals P2V2, to solve for V2. V2 equals P1V1 over P2. Plug in the values to get V2. 0.950 ATM times 1.45 liters divided by 1.0355 ATM equals 1.33 liters. We'll have a separate activity to count for class participation for this material, so look for that on Canvas under Assignments. Finally, I'll leave you with the parting thoughts of the authors.